So now in this video we're going to look at a potentiometer here. It's a trim pot. That's a 3-terminal component. There's a resistive element and a wiper that slides across there. So when you apply a voltage across both ends, you can get an output voltage anywhere along that range of voltages across the trim pot in this case. The thing is though, if that demands any current, that will throw off the voltage. So if you want to transfer the voltage, it's best to use an amplifier if you want to transfer it to a load. This is not a perfect amplifier for this because it drops about 0.6 volts. But it's transferring that voltage. The LED would not be near this bright if we wired it directly to the trim pot output right there, even though technically it should be. But there's a little resistance right there that would throw it off. Instead, we're sending a weak voltage to the base of the transistor. It's transferring it to the load right there. Other than it drops about 0.6 volts. An op amp, you would get the same voltage out. So here is a basic schematic that explains what's going on there. We got the NPN bipolar junction transistor, and we would call this circuit either emitter follower, because the load follows the emitter right there. And we also have this extra resistor just to make sure we have resistance between the emitter and ground. You may not even need it with probably most loads. But in any case, we have the load on the emitter side. Emitter follower, common collector. The collector is directly to the positive supply right there. So that gives you a common voltage right there for the circuit. Is the best way I can think of to explain that. So now in any case, whatever voltage we get in, it's going to start passing a little bit of current, but in this case probably not enough to throw off the signal voltage, and we'll explain why. We got the load, which by itself would throw off the voltage, but when a little bit of current slips through, then a lot more current, that's base to emitter, a lot more current goes collector to emitter. And so that current's going to flow and raise the voltage to 0.6 volts, less than we set there. So it's going to flow until you get to that 0.6 volts less, and then things are going to stabilize. So that would be the voltage across the load. And again, usually there's a 10K resistor here that also goes to ground, just in case for some reason, like LEDs and stuff have voltage drop. Sometimes that screws up the process. But if you have a actual resistance also going to ground, that will help make sure that you got 0.6 volts here less than you have right there. Now of course if you go down to 0 volts, there's just no voltage there. It's also 0 volts. You don't get a negative voltage or something. You have to get up to 0.6 volts, maybe 0.7 volts before the voltage starts rising here above 0. So now, this is a 5-volt circuit, but I actually was using 10 volts. I noticed I looked at my power supply, but I limited current. So we will be safe. I limited it to 20 milliamps. I think we'll look at that after this video, since it's a simple video of how setting the current on the power supply protects circuits. But in any case, we had the trim pot, as you could see on the board, pretty easily. And then to the right was the NPN bipolar junction transistor. Little jumper went to the middle terminal, the middle pin, and the way it was facing, emitter was on the bottom, and the collector was to the positive supply. I'm using a 2N3904. But in any case, there you can see we got our 10,000 ohm resistor. May not even need it at all in this video, but generally I always see it added, and it doesn't really hurt anything to have it. And so you can slide all the way down to 0 volts, all the way up to 5 volts. If you go like halfway, that's 2.5 volts, and so on. Anywhere within that range. Now, let's say you went up to 7,500 ohms of resistance from ground. So that'd be 2,500 from the 5 volts. So that would be an output, somewhere around 4 volts approximately. So that's enough to light the LED. But then that current would also be going through the 2,500 ohms of resistance if it was going directly to the LED, which would make the LED very dim, even at 5 volts total, plus 2,500 ohms. So you don't want to do that. We got the transistor instead. That voltage comes to the base, tiny trickle of current. Once current starts flowing at all, then through the base to emitter, the collector to emitter, it rushes through and builds up the voltage at that point, up to 0.6 volts, less than that, enough to light the LED. And you may be fine with just that. But the 10K resistor gives you a consistent resistive path to ground as well. And so if this throws off the voltage too much, this will stabilize it. So now really quickly before we take the voltage measurement, we'll take a closer look at the circuit. Again, middle pin there is the base. It's a 2N NPN bipolar junction transistor. It starts with 2N3904. So with the flat side to the right, the collector is on top there. Emitter is on the bottom, base in the middle. And that's pretty common for bipolar junction transistors that start with 2N, maybe even all of them. So the anode, long lead of the LED, cathode, short lead of the LED. Got to put it in the right way or it will not light up. A 220 ohm resistor is limiting the current, and that's helping us transfer the voltage from the base to emitter other than the 0.6 volt drop, which actually could be about 0.7 volts, as we will see. I actually measured this already, and so I know it's higher than 0.6 volts, but it's actually somewhere in between 0.6 and 0.7 volts usually. If you go high enough in current or low enough with base current, it might alter it slightly. So I'm actually going to pull that away, try to make sure I get the base and only the base, so we don't short circuit anything. But we do have this resistance and diode drop to ground. So if we short something, it's just going to short it up here on the higher side. Hopefully that makes sense. But in any case, there you can see a little less than 3.6 volts. So if it was 3.6 volts and we were dropping 0.6 volts, then it would be 3. So we can expect like 2.967 here if it's dropping 0.6 volts. But there you can see it's a little bit lower than that, so we're dropping a little bit more than 0.6 volts, which again, as I said, should be expected. And so yeah, 2.5 volts, that's only giving us about 2 volts to light the LED, which the LED does get a faint glow at like 1.5 volts, but it gets closer to having significant current flow through it when it's got close to 2 volts across it. So that's 1.836 across the load there. LED is pretty dim. The voltage across the LED there, you can see it's a bit lower because we need the rest of the voltage across the resistor to get the current to flow right there. So this is not very good if you want to work with these really low voltage ranges. But as you get higher, the voltage transfers pretty well. So you just got to keep that into an account that you're always losing about 0.6, 0.7 volts. And that's all we're going to do for multimeter measurements in this video. So now I'm going to add a little bonus material. We got the power supply that I'm using right there, and the alligator clips that you see there are at the ends of the wires there that come out of those 2 plugs. But any case, we got 5 volts there. This circuit, we can't exceed 20 milliamps of current unless we short circuit something or whatever. Even though the trim pot's directly to the positive supply, so that's directly to the positive supply, there's a load between that point and ground right there. So it's going to limit current. This is not a short circuit. There's a load limiting it after this. If the emitter was directly to ground, we would need resistance between those 2 points, or resistance up here as well, enough to limit current to a safe level. But again, since we have that path protected to ground, we don't. Anyways, enough rambling about that. That's the current we need. We maintain 5 volts no matter what right now, because we're not getting up to our current limit. So all we're getting is the voltage that we asked for as is. Now I accidentally had, because I used 10 volts in the last video, and I meant to have the trim pot down before this. But you can see we still only have 20 milliamps out, even though I set to 10 volts, which should be providing a lot more voltage. And that's what setting the maximum current does. So usually I have it 0.02 amps, 20 milliamps, because more than that damages LEDs. Even 20 milliamps is probably a little tough on it, but that's the maximum current they recommend. So as long as we stay below 20 milliamps, which should be fine for all these components, we will get 10 volts. I didn't mean to do that. There we go. We will get 10 volts out. But once we start asking for more than 20 milliamps of current, which would be tough on the LED, then it kicks into constant current. What that means is that if you try to get more than 20 milliamps of current, it simply lowers the voltage that it provides. and thus the load lowers the current below 20 milliamps, and it will lower it however much it needs to, the voltage that it's outputting, to make sure that we don't exceed 20 milliamps for whatever the load is. So that's why after every video I try to set the power supply to 5 volts and 20 milliamps of current, because generally that's what I assume it is set to when I just come back to the power supply after, you know, a few days of not making videos or anything. So even if I raise the voltage, if I don't need more than 20 milliamps of current, I usually keep the current set to 20 milliamps of current, for the reason that we had in this video today, where I was powering it with 10 volts when I thought I was powering it with 5. So hopefully that all made sense. Thanks for watching. Make sure you check out one of the other videos I post on screen, and check out the links down below. They all help out a lot. I'll see you in the next video.